Okay. Okay, welcome to Robotics 2. In today's class, I'm going to give you some theoretical information on the quadcopters. And my hope is that this material will complement the MATLAB Tech Talk videos. And that way, you would be able to understand the workflow and even the equations. And finally, you can have your drone flying. Now, first and foremost, let's start with quadcopters. So, quadcopters have 4 rotors, and basically they are independent. And quadcopters are different than helicopters because helicopters have squash plate. Quadcopters do not have the squash plate. So if you look at a heli, heli has a helicopter has a top rotor, and this top rotor kind of rotates. And please understand, every action causes equal and opposite reaction. So because of the rotation of the top rotor, the bottom part rotates, and to counteract the torque, you have the tail rotor. Many a times, the top rotor and the tail rotor are connected with some type of a gearing mechanism. Now, if you look at the helicopter, there are 2 ways the helicopter can advance. So there is something called as the collective pitch, which means all the blades change their pitch angle. And there is a cyclic pitch, which means as the blade goes through advance and retract, basically the angle changes. So the pitch angle cyclically changes. To achieve this, what you have is you have something called as the squash plate. So squash plate. And squash plate is a very important component of the helicopter that is used to achieve collective and cyclic pitch. Now, quadcopters, on the other hand, you can have an X configuration quadcopter wherein you have rotors over here, or you can have a plus configuration quadcopter. And quadcopters is an under-actuated system. What do I mean by under-actuated system? It's under-actuated, which means number of actuators are less than the number of degrees of freedom. So number of actuators are less than number of degrees of freedom. And the advances in microcontroller sensors, and once the cost came down, we saw a surge in the research and commercial application of the quadcopters. And what we are going to do is we are going to look at basic dynamics of the quadcopter, and we are going to study the same way as we studied the fixed wing aircraft. First, we are going to look at the kinematics, and then we are going to look at the dynamics of the quadcopter. Now, first, if you look at the quadcopter, the applications of quad are many. So you can use quadcopters for remote monitoring. Quadcopters can be used for surveillance. Quadcopters can be used for sort of agricultural monitoring. crop monitoring, yield prediction, disaster response, so on and so forth. The problem with quadcopter is, if you look at the endurance time of the quadcopter, it's low. Because if you think about the aircraft, when the aircraft is flying, the wings are creating the lift that is supporting the weight. But for the quadcopters to hover, the motors need to rotate, which means even if the quadcopter is just hovering, it's going to drain the battery. And that's why, but the advantage of quadcopter is they are extremely agile. So quadcopter or octocopter or hexacopter, they can hover at one place, they can travel left, right, or they can actually do a very acrobatic maneuvers, so on and so forth. So what we are going to do is, we are going to look at the same inertial angles and inertial frames that we studied in the case of UAVs. So first and foremost, for this quadcopter problem, let me define the position in inertial frame as X, Y, and Z. I will define velocity in inertial frame is equal to X dot, Y dot, Z dot. Then I would define the roll, pitch, and yaw angles. Roll, pitch, and yaw angles as phi, theta, psi. Now, if you look at the relationship between the body angular velocities, so body velocities, angular velocities, is equal to P, Q, and R transpose. So please understand, this is the exact same sign convention that we used in the case of the fixed wings. So the kinematic equation that relates the body angular velocity P, Q, R is equal to the inertial angular velocity 1, 0, 0, 0 minus sine theta cosine phi sine theta cosine phi minus sine phi cosine theta cosine phi is equal multiplied by P dot theta dot psi dot. So these are called as body angular rates, body rates, and these are called as inertial rates. And just like fixed wing aircraft, what we have is, we have a transformation matrix R that relates the roll, pitch, yaw with the body angles. So basically, if you want to find out the vector in body frame is equal to, so this is the rotation transformation which gives you inertial and body, where V is in inertial frame. So this is body frame and this is inertial frame. So think about it. This is going to be your rotation transformation corresponding to roll, pitch, and yaw. So basically, from inertial, you are going to have first you are gonna have a yaw, then you are gonna have pitch, and you are gonna have roll. So this is going to be the matrix that relates to the body frame with respect to inertial frame. Now, this is a very important expression. Next thing is we want to understand the dynamics. One important note to observe, if you have a quadcopter configuration, you are seeing the top view of the quadcopter. The adjacent propellers are oriented opposite to each other. So with what it means is if one prop is running clockwise, then the other two adjacent to it, then adjacent to clockwise prop will be rotating in counterclockwise. So what that means, if you have a Mambo, if one prop is rotating clockwise, the other two props which are next to the counter clockwise prop will be rotating counterclockwise. That would actually balance the torque. And I'm sure you have seen this in your Mambos. Typically, the motors are used. They could be brushed or brushless motors. So what happens is, if you have a motor, the dynamics of the motor, torque produced, is given as Kt I minus I naught, where I is the input current and I naught is the no load current. Now the voltage, so this is tau. The voltage is given as V is equal to I times Rm plus Kv, which is nothing but the back EMF per RPM multiplied by omega. So you will see this a lot. So whenever you see a motor, you will always have a kV value corresponding to motor. Now please try to understand, if you look at the motor as a purely electrical machine, you have a rotor and you have a magnetic field. So what that means is, when the motor starts spinning, it is kind of acting as a generator. So as the motor is spinning, the rotor is spinning inside the magnetic field, it is going to generate a voltage. But that voltage would have the opposite polarity of the voltage that is applied to the motor. That's why it is called as the back EMF. And it depends upon the spinning speed or the angular velocity of the rotor. So what you have is, the voltage that you need to supply is nothing but I, which is the current that is flowing through the conductor, R, which is the resistance of the conductor, so this is V, and you need to overcome the back EMF of the motor. So what that means is, if you want it to speed up, you need to increase the voltage. If you want more torque, then you need to increase the current. So next thing we want to talk about is the power requirement. So if you look at the power is V times I, and this equation, now what's going to happen is you have equation 1, you have equation 2, you combine these two equations and you will land up with an equation tau plus kt I naught kt I naught Rm plus tau Rm plus kt kV omega divided by kt square. So this is power. Even though this is the actual expression, for practical purposes, you can approximate this expression. It can be approximated as P is equal to tau plus kt IO kV omega divided by kt. So this is the expression that is used. And if you want to perform a back of the envelope calculation, and if you want to approximate this further, you can rewrite this equation as P as kV divided by kt tau times omega. Now, I want you to kind of think about what this equation implies. So, and again, this equation implies something like this. I want you to look at the equation 1. So you have tau divided by kt. Tau divided by kt gives you value of I, and kV times omega gives you value of V. So power is an approximate product of kV divided by kt multiplied by tau multiplied by omega. So this is a simplest possible equation that you can use for your motor simulation. And this equation, I have seen this equation being used not only in the quadcopter dynamics, but even where you are using a simple DC motor and you need to perform some back of the envelope calculations to make sure that the motor dynamics is appropriate. So a quick recap. If you look at the dynamics of the quadcopter is a rotorcraft. It has 4 rotors. If it's a hexcopter, 6. If it's an octo, it's 8. The frames are going to be the same. You have the inertial frame, you have the vehicle frame, you have vehicle 1 frame, then you have the body frame. And what we have here is we have a relationship between the body rates. So coordinate axes are same. Again, north is down. North is x, east is y, z is down. And you have these inertial rates, which are again the derivatives of inertial angles. And you have this transformation matrix. And finally, just like our coordinate system that we studied in fixed wing, we have a direction cosine matrix which relates the inertial quantities, a vector in inertial frame with the vector in the body frame, and you have the transformation that takes you from inertial to vehicle 1, vehicle 1 to vehicle 2, vehicle 2 to body. Everyone understood this? Remember, this is something that we did first. So this transformation will take us from inertial to vehicle 1. This transformation will take from vehicle 1 to vehicle 2. And the last transformation will take from vehicle 2 to body. Everyone with me so far? So whatever we have derived, the only thing that we are not looking at is we are not looking at the side slip velocity, or we are not looking at the angle of attack. So basically those frames we ignore. So we are going from inertial to the body. So next two frames, which is the stability frame and wind frame, that we don't consider for quadcopter, but all other frames are the same. Now, if you have a quadcopter, if this is clockwise, then these two need to be counterclockwise, and this has to be clockwise. And then the orientations are opposite to each other, and they typically use the brush DC motors or brushless motors. For the motor dynamics, torque is equal to the torque constant multiplied by the change in the current. Voltage is equal to the voltage drop across the resistance plus the back EMF that is generated as the motor spins. So kV is an important parameter for the brush and brushless DC motors. Okay. And then what we do is we can come up with an approximate equation for the power, which is nothing but P is equal to V times I. So substitute equation 1, equation 2, and now you have this equation 3, which gives you power is equal to voltage multiplied by current. Any questions here? Next thing we are going to talk about are the forces. Now, if you look at the forces, the basic fundamental principle is whatever is the lift generated by those props should be equal to the weight of the quadcopter so that the quadcopter can hover. And what that means is if you want to use a fluid dynamics approach, we can say that the P times dt is equal to F times dx. Now, what that means? It means that the energy multiplied by, basically this is energy per time, power, multiplied by time is equal to the force multiplied by displacement. So this force is the force generated on prop. And displacement is the air displacement. So this equation can be easily written as power is equal to thrust multiplied by air velocity. And this is given by T times VH. Now, one thing I want you to understand is we are going to make some assumptions. That first assumption is free stream velocity is close to 0. What that means is, unlike the fixed wing aircraft, where the aircraft is flying through the air, you are going to have some type of fixed, some type of a free stream velocity, which is the velocity of the air at infinity, which means the air flow. But for the sake of simplicity, we are going to assume that the free stream velocity is 0. Now we are going to use the equation for momentum balance, and that equation is given as T is equal to 2 times rho times A V H square, and this comes from the momentum theory. And you can this is an approximate equation from aerodynamics, but you can actually make this equation even more complicated if you use the computational fluid dynamics or advanced aerodynamics theory. But this is a very simple equation that actually gives you the relationship between the thrust and the momentum. So VH, which is the velocity for hover, is given as square root of T divided by 2 times rho times A. And I need to tell you here, T is thrust. Now, rho is the density of the air. And A is the area swept by the rotor. So, and again, what's going to happen is thrust can be related to power kV by kT times tau times omega. This equation can be written as kV divided by kT, and I'm going to replace tau as k tau multiplied by T multiplied by omega, which is k tau is the coefficient of thrust. So k tau times T is equal to torque. Thrust. And this is the thrust coefficient. So now all said and done, what you can do is you can substitute the equations that we have derived. This is 4, 5. And finally, you come across this equation, and this equation is very commonly used. I'm going to just write this down. I'm not going to derive this. We can derive this, but that is not needed because finally it's a constant, 2 rho A divided by kT omega square. And this is a very famous equation that is used, which is K times omega square. What that means is the thrust. T stands for thrust, tau stands for torque. Thrust given by the prop is equal to a coefficient K, which depends upon these factors, and A is dependent on the prop geometry. KV, let me see, this is KV times K tau, KV times K tau, KV times K tau. So KV and K tau, they are dependent on motor, and then KT is also dependent on motor, and then this stands for the speed of the motor, speed. So that's why whenever you are designing a quadcopter, typically when you choose the props, manufacturer will give you the recommendation on the correct motor sizing. You cannot use a prop, any prop with any motor. Just like you cannot use the Hummer transmission with a Civic engine, you need to make sure that the prop and the motor, they are balanced. Otherwise, it will not work. So finally, what we're going to do is we have 4 motors and we want to find out the total thrust. Total thrust is given as summation of I is equal to 1 to 4 Ti, which is K 0, 0. This is omega 1 square plus omega 2 square plus omega 3 square plus omega 4 square. So this is basically the force in the x direction, force in the y direction, force in the z direction is equal to, we need to sum, there is no force in x direction, no force in y direction. When the motors spin, we square their speed and multiply with a constant k, and then that gives me the total thrust that is acting on the quad. So for an example, if you have this quad and there are 4 motors, then you're gonna have this will be k omega 1 square, k omega 2 square, k omega 3 square, and k omega 4 square. Now please understand, air is present, so you are going to experience some type of a drag, and that drag force is given as, so you would have a drag force, and drag force is given as minus kd x dot minus kd y dot minus kd z dot. Now what that means is, I want you to quickly look at this chord. This quad, let me set up the coordinate system. This is x, so this is z, and this is y. And then what's going to happen is, as the quad is hovering, if it has a non-zero velocity in the z direction, it's going to have the drag force. If it has a non-zero velocity in east direction, it will have a drag force. And if it has non-zero velocity in x direction, it will also have the drag force. So you are going to have, this is, please note, this is north, this is east, and this is down. So one thing, it is very important to understand that the drag force is defined with respect to inertial frame or inertial velocities. So what that means is x dot, y dot, and z dot, those are not the body velocities, but those are the inertial velocities. Next thing, what we want to do is, we want to find out the torque. So we looked at the motors, we looked at the forces, and this is a simple propeller theory, that amount of work done by the prop is the mass of the mass of the air multiplied by the gravitational constant. So that is basically gives you the force multiplied by the displacement. And then what you get power, which is the thrust multiplied by the air velocity. And this equation I did not derive, but this equation for thrust comes from momentum balance. And just to give you a quick understanding of what this momentum balance is, if you think about thrust is an equation for force. You get mass quantity here, then you get the volume quantity here. Volume quantity gets multiplied. Okay, I can actually derive this a bit. So if you perform the dimensional analysis on this, please note rho is equal to kg divided by meter cube multiplied by area. So A is meter square, and VH is equal to meter square plus second square. So when you multiply this, what you get is, you get the equation for Newton, which is kg meter per second square. And you get this 2 from because of the prop factor. So this. The next part is if you want to find out the total force, please understand the force acting on the quadcopter is a vector quantity. You have the thrust in the x direction, thrust in the y direction, thrust in the z direction. That is equal to the summation of all the thrust by the motors. Please, this equation is valid when you have the configuration which is shown over here. So you have the props and the rotor which are perpendicular to the airframe. In some cases, there are quadcopters or hexcopters where the rotors are tilted. And when the rotors are tilted, the system is no longer underactuated because you are able to generate the forces in other degrees of freedom. At that time, please understand, you are going to have a component of force in x direction, you are going to have a component of force in y direction, and you are going to have a component of force in z direction. So if your rotors are not vertical, but they are tilted, then you will have some component of force in x direction, some component of force in y direction, and you will have obviously some component of force in z direction. Yeah. How is it mitigated in tilt rotor aircraft? Oh, tilt rotor. Okay. So tilt rotor, if you does everyone know what a tilt rotor is? So the idea is you have a helicopter. The helicopter biggest advantage is it can hover in place. But unfortunately, helicopters cannot go fast as fixed wing aircraft. Helicopters are not very efficient because the amount of lift that is generated is completely by the rotor. If you have an aircraft, what happens is the aircraft can go very fast, but they cannot hover. And in terms of agility, if you look at the tilt rotor, the turning radius of the tilt rotor is much less than the fixed wing aircraft. So what happens is, as you take off, you have two rotors. As you take off, you have two rotors, and those are vertical, and the airframe takes off vertically, and then in transition flight, those rotors, they basically tilt forward, and now those rotors act as a prop, and then you have converted a helicopter into a fixed wing aircraft. And again, if you study purely the dynamics of the tilt rotor aircraft, when the tilt rotor aircraft is hovering, it is treated as a helicopter. When the tilt rotor aircraft is into full flight mode, fixed wing mode, it is treated as a plane, but the transition dynamics is quite complicated. Because what you want to do is you want to make sure that the helicopter it can transition from a heli mode to a fixed wing mode. There are certain configurations in the fixed wing aircraft that are more amenable to tilt rotor. So I would encourage you to look at, there are two predominant commercially available designs. One design is V-22 Osprey, which is a military carrier. And there is a civilian version, which is Bell Augusta 609. And again, both of these are very successful tilt rotors. Then if you are looking at the transitioning aircraft, there is a Parrot X-plane that I want you to, if you have a time, you can take a look at it. That dynamics is very interesting. So basically, it's like an X-plane, and actually I have one. So you have a plane, and it is not a tilt rotor. The rotor doesn't tilt, but the whole aircraft tilts. Then you have this another plane. So these are the wings. And then what you have is, you have prop here, So this is called as the X-plane configuration. So what happens is, and actually the flight control system for this plane, this X configuration is very nice. So what happens is, it takes off like this. It takes off like this. And then what you can do is, you can transition it in plane. So how does that transition occur? Can someone guess how this transition occurs? Basically, this takes off, and then the amount, these rotors, the bottom rotors slow down, top rotors speed up, and basically the aircraft flips. And in that case, the bottom rotors and top rotors, the speeds get matched, and you have a flight mode. When it wants to come back, again, the bottom rotors speed up, top rotors speed down, so it flips up, and then basically the whole transition comes down. So this is the X-plane configuration, and it's a beautiful flying plane. So and it can achieve transition in flight. So you can actually okay. The reason I was attracted to this configuration is, first and foremost, it brings good of both worlds. So basically, if you want a plane to hover at one place, you can have the X-plane configuration hovering. And then if you want to achieve high endurance, you can flip and you can achieve high endurance. So, and actually the longer time or for surveillance, this is actually an excellent frame. So please look at, and this is actually commercially, it's a toy. It's available for $100. So Parrot X plane. Anyway, but you can, I have also seen something called as the stop rotors. And actually we designed and flew one. The idea of stop rotor is, what you have is, you have a rotor, and this whole thing takes off as a helicopter, and in flight, basically it transitions into a plane. So the rotor stops, and then you have something like prop here. So this becomes a puller prop configuration. So this is the prop. So basically you have these, this is actually rotating, that is also rotating. So you have a top spinning rotor, top spinning prop, and bottom spinning rotor. That gives you the hover. And as soon as it takes off, basically it does the roll pull up maneuver. And in case if you are wondering what that maneuver is, have you seen the movie Top Gun Maverick? Okay, so no, then watch that movie. So basically what happens is, the aircraft basically goes up like this at a very high angle of attack, rolls, flips back, and comes down and comes up. That's a very classic maneuver that is done in fighter planes. So this aircraft can perform that maneuver and get transitions. So from fixed wing, from the helicopter, so basically it will do like this. So this will be the flight path. Will take up. And then there is again coaxial. We also built coaxial. And coaxials are very famous toys. So you have one rotor that is spinning clockwise. You have other rotor that is spinning counterclockwise. And why do we need two rotors spinning opposite? Because action and reaction. So you need to cancel the torque given by the top rotor with the torque given by the bottom rotor. But both of these should provide the thrust in the same direction. If you want to make it a little bit more efficient, then basically you add shrouds or rings that actually directs the airflow and minimizes the eddy current loss or the vortices here, and that basically generates the lift. It makes more efficient. And to be honest with you, if you're a hardcore aerospace engineer, you study all these in a lot more detail. But as a roboticist, what we are interested in, we are interested in understanding the basic kinematics of an airframe, basic dynamics of the airframe, what are the forces and moments that are acting, and finally design the appropriate flight control hardware or control so that we can achieve the mission. Okay. So we finished with the drag force, we finished with the thrust force. But at the end, let me tell you, no matter what airframe you choose, the kinematic equations are going to remain the same. The frames are going to remain the same. Only thing is, you'll analyze that as a helicopter, analyze as a plane. You may look at the transition, but the frames are going to remain the same. But the equation for forces and moments and torques will be different. Other than that, everything else is the same. So whatever we studied for the fixed wing can be extended to the rotary wing. So torque. Any questions from anyone? Okay, torque. So to find torque, what we need to do is first we need to find out FD, which is a drag force, which is 1/2 rho times coefficient of drag multiplied by the area multiplied by the V square. So this is the drag force. So torque, because of the drag, which is given as tau d, is given as 1/2, and this is the exact same equation that we studied in the case of fixed wing, rho times CD A times V square, and finally this equation comes as B times omega square. Now the total torque is given as Tz is equal to B omega square plus I times omega dot. And this equation is nothing but T is equal to I alpha plus B times the speed of the angular velocity. So if you think about it, what you have is you have the T is equal to I alpha, which is the Newton's law, and then you are adding the drag force to it, and that gives you, or the drag torque to it. So this is the drag torque. And this is the total torque. And this is the inertial effect, inertial torque. So if I want to extend this to the total torque in your direction, that is given as B omega 1 square minus omega 2 square plus omega 3 square minus omega 4 square, depending upon whether you are spinning clockwise or counterclockwise. So 1 and 3, these are 1 and 3, are spinning clockwise. 2 and 4 are spinning counterclockwise. Next thing, I need to find out the torque in the roll and pitch. So torque in roll is summation of radius crossed with the thrust, which is L K omega 1 square minus K omega 3 square. And this equation is LK omega 1 square minus omega 3 square, where L is the distance between the motors. Similarly, we can actually find out, this is the roll torque, roll. Similarly, we can find out for the pitch, T theta, same thing, is equal to L times K omega 2 square minus omega 4 square. This is for the pitch. So now if you think about it, please understand, we have the torque equation in the yaw called yaw direction, torque equation in the C direction, and torque direction in theta direction. So what we have is, if you look at this airframe, so actually I need to draw. This has motor 1, motor 2, motor 3, motor 4. And what I'm going to do is I'm going to set up my coordinate system. This is my X, this is my Y, this is my Z, and my X is corresponding to roll. Y is my corresponding to pitch, and Z is corresponding to yaw. So if you look at the roll is omega 1, omega 3, omega 2, omega 4. And now what you have is, you have your props here. And this is the plus configuration. So it's actually quite simple. So as you can see, this is the roll 3 and 1. Roll is 1 and 3, 1 and 3, and 2 and 4, 2 and 4. And then if you want to find out the torque in the yaw direction, you have to sum them all. Everyone understood this? The next part is we need to derive the equations of motion. Okay, one thing I want you to understand is, after we derive all this, I will actually walk you through the MATLAB code that I have written that will simulate this quadcopter. So basically, this is the bare minimum simple dynamical equation of a quadcopter. But I can tell you, once you understand this simple dynamics, you can play with this equation and have that quadcopter perform super complicated maneuver. This works very well. So equations of motion come from the Newton's law. Force is equal to mass times acceleration. So equation of force is equal to mass times acceleration. So I'm going to have this equation m x double dot. X is the acceleration vector, which is given as, first we have to consider the gravity. Gravity is only in z direction, weight of the gravity, plus we have the thrust, plus we have the drag force. So now this equation is expressed in multiple coordinate frames. So let me write this down. So this is the drag force in multiple frames. And I will write these frames down. This is the drag force, which is given in inertial frame. Then you have the thrust vector, thrust in body frame, R is the rotational matrix, that goes from body to inertial, and this is given in inertial frame. And these are inertial accelerations. So please understand, just like robotics 1, just like the fixed wing aircraft, just like all the dynamics that we have studied so far, force is equal to mass times acceleration. This expression needs to be in the inertial coordinate frame. Inertial coordinate frame is the fixed frame, and we are not looking at Einstein theory of relativity. We are going to derive Newton's law in the inertial frame. So for that, the drag force needs to be in inertial frame. Thrust force is expressed in the body frame, that needs to be mapped to the inertial frame. So R is the rotation transformation that will take from body to inertial. This is the force because of the gravity. Gravity will always point out towards the negative z direction. So you will have this minus mg. So, or it can have plus depending upon how you treat it. So if your z is going down, then it will be plus mg. The next equation, we have to look at the equations of torque, I omega dot plus omega cross I omega is equal to torque, which is the Euler equation for rotational dynamics. Remember this equation that we studied in fixed wing? I theta dot, I omega dot, which is I theta double dot, I omega dot is equal to omega cross I omega is equal to tau, which is nothing but the angular principle of angular momentum. Just before I go any further, everyone remembers that I derived this equation when we talked about the fixed wing. Remember this equation? So what I'm trying to say is the basic kinematics and basic dynamics is the same no matter what airframe you choose. Now, only difference you will see is I is going to be different, equation for torque is going to be different, but everything else would follow. So, omega dot is omega x dot, omega y dot, omega z dot. And then that equation can be written as, I'm going to take tau minus omega cross I omega multiplied by I inverse. So what I did, I took this equation, I took omega dot on one side, I took omega cross I omega on the other side, sign change, and then I inverted I, where I is mass moment of inertia. Now we are going to find out the mass moment of inertia at the centroid. So I is the mass moment of inertia at the centroid. So I is equal to Ixx 0 0 Iyy and Izz. This is principal axis of inertia. And I inverse, since it's a diagonal matrix, that is given as 1 divided by Ixx, 0, 0, 1 divided by Iyy, 0, 0, 0, 1 divided by Izz. Okay. The next thing is a little bit complicated. So we really want to carry out this math. And for that, we have to use the cross product. And I don't know if I should actually, let's see, I will do it. I'm just gonna do it once because there might be some students, they might not be familiar with the cross product term. So I inverse, so I'm gonna take this equation and try to expand it. 1 divided by Ixx, 0, 0, 0, 1 divided by Iyy, 0, 0, 0, 1 divided by Izz. Multiplied by tau. Tau is going to be something like tau x, tau y, and tau z. So there will be something like tau x, tau y, and tau z. So tau x, tau y, tau z. Yeah.
The I inverse also have scaling factor of Ixx into Iyy into Izz.
Ixx into Iyy into Izz. Let me see. Oh, you mean the determinant? How do you find the inverse? I'm seriously asking, how do you find inverse?
MATLAB.
You first find the cofactors. What do I mean by cofactors? So you have 1. So you first find cofactors and they become Xx, Izz. Happy? In case if you are wondering what I did, how do you find inverse of a matrix? To find inverse of the matrix, what you need to do is you need to find the cofactors. And depending upon where the location is, you get positive or negative sign. So for an example, here you cross this, take this product that goes over here, then everything is 0. Go here, cross this, take this product, and then cross this and take this product. Since that is first row, first column, it's going to be, it will be multiplied with +1. That is second row, second column. So that will be multiplied by +1. And that is third row, third column. So that would be multiplied by +1. Everyone understood this? Remember cofactors? Okay. Then what you have is minus omega cross I times omega. And this is a big equation that I need to write this down. This becomes, I'll solve it here. Omega cross I omega is nothing but I j k omega x, omega y, omega z I omega ixx omega x iyy omega y izz omega z, and you have to expand this whole thing into cross product, and then you get this equation omega dot is equal to tau phi. So this is tau phi, tau theta, and tau psi. Tau phi ixx inverse, tau theta iyy inverse, tau izz inverse minus iyy minus izz divided by ixx omega y omega z izz ixx iyy omega x omega z ixx iyy divided by izz omega x omega y. This is a very important equation, and actually what I'm going to do is, for my own satisfaction, I'm going to derive this equation one more time. I'll tell you why I'm going to derive this equation. If you were to, for example, if you go into some robotics industries, and then you are looking at some exotic aircraft, which is not like quadcopter, which is not like a fixed wing, some random combination of quadcopter, fixed wing, or maybe it's a kite, you don't know. This equation, no matter what airframe you choose, you will use it. So what I'm going to do is, in my next class, next Thursday, there will be someone from MathWorks coming and talking. But next Tuesday, I would actually derive this equation, which is written over here, omega dot is equal to that big expression. Because at the end, what you are going to do is you have the equation for dynamics, translational dynamics, you have the equation for rotational dynamics. You use those equations, and then you can simulate your quadcopter. So, and then what I'm going to do is I'll walk you through the MATLAB script, and then we will look at the control, PD control, and all the simulations. But this stuff is very important. So we'll stop here and we'll continue in next class.